Good afternoon. Last time we started talking about dynamic logic in CMOS technology. So in this circuit, you use an N block, and then put here maybe like this pre-charge block, and then this is valid in evaluation cycle. So that's how we implement the circuit. So since the pull-up, this is called pull-up. It's called pulled up. The pull-up is not always pulling up, so therefore, output voltage can drop to 0 if this is valid, for example. So this can be pulled down to 0. So that's kind of the advantage of the thing here. So this is used for pre-charge, but then it turns off during the evaluation. Okay. So off during the evaluation cycle. So that's an advantage. With the help of this advantage, output can reach down to 0 volt. Okay. CL can be discharged down to the ground. So what we said that this circuit has a problem as if you connect one another block, similar block, because if you have, let's say, more than, let's say, one transistor on the pull down cycle here, so this pull down is going to take time, and therefore there's going to be delay here, more delay. Why? Because 3 transistors. So if you think about each transistor to contribute a resistance, so RC time constant in terms of that, you will have more time taking, because the resistance is going to be higher. 3 of them are coming in series. So due to that, if one of them is evaluated, let's say this is the case, for this case we are talking about now, this case. So for this case, the evaluation of going low is going to take time, but the next circuit doesn't know that. So the next circuit thinks that the input or this node is already high, so thinks that it's going to remain high, and then it discharges this capacitance very fast. And since it does that, we assume that the similar CL is also here. Since it does that, then it's already discharged. But then, Vout1 comes to low, and that means, the next inverter, this is in fact the inverter, cannot charge back. So input is low, but output is, is also low. So due to that, there's a mistake in the evaluation. So this is the reason for this problem is that the default value here at this node, the default value is turning this on and discharging this transistor. So we don't like that. So we have to use something, in here to prevent that problem. And one way to prevent that problem is to use, an inverter here. So if we use an inverter here, then the default value is not going to be, turning this next gate on. So the default value is going to be off value. Okay, so if the same thing happens here, let's say, we have the same problem here, and then we put here, just, to increase that delay, B, which is connected to this one. So let's do exactly the same thing. And pre-charge and evaluation cycles. So we need to put here also for the next gates an inverter. Okay. Then the default value does not turn on the transistor. Okay, so that's the idea. So let's solve the circuit right now to see what happens. When VA is low, during the evaluation, let's draw this again. During the pre-charge, this is pre-charge. During the pre-charge, the output one, this is, let's say, PZ, and this is Z, this is PY, this is Y. Okay, so PZ is going to be pre-charged, which is going to be VDD, but then Vout1 is going to be low. So this is going to be staying low here. And similarly, Vout2 is going to be also low. Okay, so if we draw here PZ or PY2 or PY here, and then here PZ, then initially this is going to be high because pre-charged up. So during the evaluation, what is going to happen? Since that's 0, it will remain in here. So will remain in here. And then this one, however, since the output is here is 0, the node Py is going to be remaining at Y, and via output 2 will go to low again. So Py will remain in here, and then this will remain in here. So this will remain in here. So during the pre-charge, again, VR2 and VR1 is going to be like this. But since A is now high, during the evaluation, PZ will go low and VR1 will go high. So let's say this is going to be going high, but it will take time. Takes time because of the 2 transistors here. So, you know, this one during the evaluation, you know, it will wait until this one to go high, then this goes high. Why do I have it differently drawn? So this will remain in here, and then it will go to high. You know, there's going to be, this has to wait. Okay, so the correct evaluation will be correct then. And then, you know, after this, during pre-charge, this will come back, and then this will come back. Okay, so, but, you know, VR1 and VR2 are both correct. So these are going to be correct. Of course, we have like one inverter and then the second inverter. Therefore, VR1 and VR2 look similar, so we don't see an inversion cycle here. But this is a correction method. So, but we don't like this so much because, you know, non-inverted outputs are not possible. So we don't like it. Only non-inverted outputs are possible. So, I mean, this is a solution, but we don't really like it. And then, you know, extra inverters. You know, we don't like extra inverters to put. So another nicer solution is to use NP domino logic. So what does that mean? So here the solution is, this is N block, and here we use P block, and then we use N block again. So the default value here, which was high, is keeping the next gate turned off. So next gate is going to be off. Since this is the P block, then we take the output from here. Remember, you know, if it is N block, we use a resistor here, for example, for plug. But if it is P block, then we use a resistor here and then use this as V out. So similarly, here we need to take the output from here. Okay. So this is pre-charge. This one is pre-discharge. And then this one is pre-charge. So this is the way that we can connect the circuit blocks next to each other, and then everything, operates properly. So first, use an N block and block case, and then P block, and then N block. Okay. So if you need to go to an N block, to drive and N block. For example, circuit forces you to make such a connection to N block from this node. Then you need to put the inverter and then, change your design logic accordingly to work properly. So I guess you understand the idea. So dynamic logic, how can we design this logic? Using dynamic logic. So we can do this at once without using another circuit block. Let's say that this is equal to Z. Okay. So in the dynamic logic, do this. Oh, by the way, in this one, you need to notice that here, clock bar is used. Okay, that's how it works properly. So when the clock is high or clock is low, clock bar is going to be high, so it will be pre-charging this node. So this pre-charging happens in this cycle. So that's how we use it. So we can draw the N block here. So this is the pre-charge thing. So clock is coming here, and then we just need to construct the N block. And B, this is A, B, C, and D. And then this is clock again. So the output is going to be from here. So that's the dynamic logic. So we will see this as Z. So if you want to combine this, let's say this output, let's make this a little bit more interesting. Okay, so let's say this is Z block, which gives us Z. And then A, B, C, D here. Okay, and let's, sorry. Let's put this into an AND gate with E. And then let's put this with an OR gate, F, okay? Just for fun. How can we do this in this logic? So, since this is N block here, N block, so we need to use the next gate as P block. So the next gate should be P block. Therefore, we put here clock bar, first of all. And now, how can we implement NAND in P block? Remember NAND gate? If you remember the NAND gate, how can we draw the NAND gate? Maybe I'll do this. The NAND gate is implemented like this, right? So this is the AND block part. This is the P block part. A, B, A, B. Right? So we need to take the P block part for the NAND gate. So therefore, for the P block, we have this. And this output goes here, and the other input is going to be E. And then we have here clock bar, and the output is taken from here, and that's called, let's say, Y, and then X. Okay, so this will be Y. And the Y output is going to be connected to a NOR gate. And since this is P block, we need to have an N block next. So the next N block needs to be an NOR gate. So the NOR gate is again, oops, sorry, like this. Oops, sorry, I keep putting that. So this will be your clock. This output will go to one of the inputs, and there's going to be pre-charge node, VDD, and this will be PMOS transistor. And here we will be also entering this clock. And the output, or this input, is going to be F, and output is going to be taken from here, and this will be your X output. That's how you design the circuit. And what is the advantage of the circuit? You know, it synchronizes the outputs together with the clock, and then you know, it prevents clock skew problems. So maybe I should do this. So this looks like bar here. I shouldn't do that. Okay. So and this is a nice solution. Is that okay? So you know, there are other solutions here for this problem. Instead of NP domino logic, there are maybe other solutions. There are other solutions like 4-phase clock. Okay, covered in 413 VLSI design course. Okay, so this is, I guess we'll be, covering this much. There's one other maybe logic that we should talk about, and that's pass transistor logic. The pass transistor logic is totally different than what we have seen, and we need to first understand the use of switches here. So this logic is made with switches, and we can implement different things. But first, let's look at the use of transistors as a switch. We can use NMOS transistor or a PMOS transistor as a switch. So if you use PMOS, for example, it's also possible. In and out. So IDS VDS graph. Why is it given IDS VDS graph? So if the input is VDD, what happens? If the input is 0, what happens? Okay, let me just do it the way that I know. If the control signal, I mean, we know that this transistor, we used it as a switch. And we kept saying that in an inverter, for example, we said that this is like a MOS switch, and then this one is like NMOS, PMOS, VDD, and this is V out, okay? And then when we do this, it's nice, and the PMOS, nicely transmit the signal, so output reaches to 0, so 0 volt to VDD swing. Okay, so but we don't use this. I mean, we don't do this. We can think that this could be also possible, but no, we don't do that. I mean, first of all, if you do this, this is not an inverter. It will be just a buffer. It will operate as a buffer, but we don't like this. So this is, maybe I should just erase this one. Okay. So there's a, we can see why this is happening or not happening. So if the control signal is applied here, let's say, I guess control is VDD, so that we turn it off or turn it on. So when it's on, we think that this is going to be switching. So if there's a 0 volt here, so V out, okay, what is going to be V out? What is going to be the voltage at the output? So, in order to understand this, maybe we should just put here C load. It's always useful to have a C load and then discharge, and charge that capacitor to understand what is happening to the voltage. So if there was, let's say, initially VCL initially VCL 0 plus is equal to, I don't know, 5 volts, okay? What happens to VCL at infinity with this case? So the capacitor will be discharged through here because this is ground. So we can call this side as drain, this side as source. Okay, so maybe the base here is ground, connected to ground, and then we base is ground. Okay, the smallest voltage that we have. It can be connected to source, but the source and drain will be switching here in the device, because this is unilateral. I mean, bi-directional device, right? And we have M plus and M plus, and it's not like BJT. Dopings are same here, same dopings. Not like BJT. So therefore, bidirectional. Device. Okay, so we have that. So here, since this is the gate and that's the source, gate to source voltage, as you see here, is what? With this is V drain to source, V gate to source minus V threshold of N. So IDS, that's how we draw our circuit. Maybe I shouldn't do it this much, just to be more consistent and correct. So this is where we gate to source is equal to 5 volt graph. So remember, I'm trying to do this as accurate as possible. If this is VDS is 5 volts, and this one is equal to each other, gate to source is 5 volt, and this one is 1 volt. So this one is going to be VDD minus VTN, which is equal to 4 volt graph, right? I mean, just to be accurate here. I mean, for this question, we don't need to calculate that, but I'm trying to draw this nicely. So what happens? I mean, at infinity, at steady state, okay? At steady state, the current here will be 0, right? ICL will be equal to 0. So that ICL or minus ICL is equal to what? I drain to source of N. So that should be equal to 0. So that's why we are going to be here. This is the operating point. Okay, because gate to source is 5 volt and the current is 0 at steady state. Therefore, VDS, so VDS is going to be equal to 0 volt. This is VDS. So what about V out? V out is going to be equal to V in plus VDS. Therefore, it's going to be equal to 0 volt. V out. So this is a switch. If the input is 0 volt, output is going to be 0 volt. So this can be nicely considered as a nice switch here. This is in, this is V out, and this one is control, which is VDD. Okay, this is like a perfect switch for zero input. The problem actually occurs if we want to use this to transfer high voltage. Now, if we want to transfer a high voltage, we can still, make the same argument. And the same argument is what? What is the same argument? The same argument is that we will be assuming that first, assume that VCL is at the other extreme. VCL initially at 0 volt. So, and at steady state, it will be charged. Be charged up to the voltage where ICL becomes 0. Okay. So, we will be saying that this is going to be charged. And then since this one is going to be on, transistor Mn, and then it will be charged. And it will be charged through here. Okay. What is the state of the transistor here? First, we can define the drain and source. We know that now the current is going from this side to this side. Therefore, we will call this thing drain. This is going to be source. And this is it. And typically, this bulk is connected to ground here. Okay. Because it can go either way. So we don't connect the source or drain because that keeps switching. So we put that switch voltage to the lowest value. And this is the gate. Okay, so what is the state of the transistor here? Note that Mn is in SAT. Why do we say that? Because the drain to source of N is always larger than V gate to source of N minus VTN. Why? Because V gate and V drain are equal to each other. So we say that V drain minus V source is larger than V gate minus V source minus VTN. And then here, maybe we can just, cancel out the sources. So this will look like V drain to gate is always larger than minus VTN. What is V drain to gate? They are both VDD, therefore this is 0. Okay, so this is always the case. So Mn is in SAT. Okay, so that's very interesting. So if Mn is in SAT, then IDS of n is going to be equal to Kn divided by 2 V gate to source of n minus Vtn square. And we say that this is going to be until ICL is equal to 0. Therefore, if this is the case, I drain the source of L is going to be, not L. I drain the source is going to be equal to 0. So if this is 0, okay, if IDS of n is also equal to 0, so what is V gate to source of n? Vtn. Vtn. That's interesting. So V gate minus V source is equal to Vtn. What is V gate? VDD. What is V source? V out. So what is V out? VDD minus Vtn. So V out is going to be equal to VDD minus Vtn. So Vtn is going to be here. And then there are other interesting things here. So V in, oops. V in is equal to VDD. V out is equal to VDD minus Vtn. And Vtn is not equal to 1 volt here. Note that Vtn is not equal to Vtn, where V gate to, V source to bulk is equal to 0. As you know from your previous courses, Vtn is going to be equal to Vtn 0 plus, maybe you don't need to memorize this, but just for you to see this, V source to bulk plus 2 phi f minus 2 phi f. And that would be the case. So if this is originally 1 volt, this is going to be what? V source to bulk is equal to V out. So output will be depending on the output threshold voltage. So V out will be equal to VDD minus Vtn. Not only that, but also gamma something, which is square root of V out plus 2 phi f minus 2 phi f. The point here is that this is going to be about maybe, this can be 4 volts or not even, if this is the case, then this is going to be 1.5 volt. Therefore, V out is going to be equal to about 3.5 volts. Okay, even lower than that. So the summary is that NMOS cannot transmit high voltages nicely or fully. Okay, so then there's a problem, you know, of transmitting the high voltages here. I hope this is clear. We will look at the PMOS, and that's, I mean, of course, for an inverter, we like this, you know, because it transmits the low voltage nicely, NMOS. But we'll see that PMOS transmits the high voltage nicely. And then that's why for the P block, I mean, for the upper portion, which is connected to VDD, we use the P block, P transistors. Okay, so I guess I can continue here or just give a break. Let me give a break here, and then we'll just, you know, finish the rest of the slides today and then stop. Is that okay? Any questions? Okay. Okay. We have seen last hour that the NMOS can be used as a switch, but it's not maybe very efficient in transmitting high voltages. Now we will look at the case for the PMOS as a switch. Now for the PMOS, we can draw again the device. So let me draw it this way. And now for this switch, to turn it on, so it becomes on when we apply here 0 volt. Okay, to turn on. So if this is 0 volt, and let's look at then the case where the input we in as initially maybe 5 volts. 5 volts. What happens to V out? You know, we'll look at this case. The V out. In order to calculate that, we will again use this trick of charging a load capacitor. So if we have a CL here, this will be charged through here. Okay, if VCL is equal to 0 initially, and then it charges through MP transistor. Let's call this thing MP transistor until ICL becomes 0 amp. Okay, so here we can determine the drain and source of the transistor. Since the current is in this direction, we call this thing source, this is drain, and this is the gate. So, you know, we can look at again the curves here. So if we look at I, this is V source to drain, this is I source to drain, and the line again is equation is here. This is the line. This is V source to gate is equal to 5 volt line. So this one is going to be VDD. And then this node is going to be the voltage, just to draw it precisely, minus VTP. Okay. And since that's the source to gate, because source is 5 volt, gate is 0 volt, source to gate is 5 volt, and here this is the operating point now. You know, this is the point where ISD is equal to 0. So if this is the case, then V source to drain is also equal to 0. Okay, so V out, we know that V out is equal to V in minus V source to drain. This is V source to drain. And since V source to drain is equal to 0, so V out will be equal to V in, which will be equal to 5 volt. Okay, so the conclusion is that you know, PMOS transmits high voltages fully. Okay, so now we will look at the other case. By the way, the bulk is going to be connected to ground here. So the other case is, sorry. This is connected to VDD, the highest voltage. If we do the same thing, this time again 0 volt, and input V in is equal to 0 volt. What is V out? Okay, here is again VDD. We can put this CL here, okay, and then say that VCL CL is initially 5 volt, then it will discharge through MP until ICL or minus ICL becomes 0. Okay, so here we can write which side is drain, which side is source, because the current is in here. For the PMOS transistor, we say current goes from source to drain. So that's the current direction. So this is gate, of course. So now we know that for this case, isolate this here. For this case, For this case, what is the state of the transistor? MP is in SAT. Why? We can check if source to drain, what happens? Is it larger than V source to gate minus VTP? So we source to gate V source minus V drain, V source minus V gate minus VTP. So these are gone. And source and drain is equal to gate. Therefore, it's always 0 is always larger than minus VTP. So SAT. So if it is SAT, then the equation here that we need to consider, the equation is going to be I source to drain of P, which is equal to, it should be 0. It should be equal to Kp divided by 2 V source to gate minus VTP square. So if that's the case, then V source to gate should be equal to VTP. So what is V source? V source is 0. So what is V out? V out is equal to V in plus V source to drain. Source to gate, source to drain, or source to gate, because the other side is ground. So in any case, if you look at this, V out will be equal to VTP. Okay, so it cannot be discharged down to 0. So we can say that PMOS cannot transmit low voltages. Fully. So therefore, what we do is typically use them together. So we use CMOS transmission gate. This is, so we will be applying here control bar and control. So if you do this, then if V in is equal to 0 volt, output is going to be V out is going to be 0 volt, thanks to NMOS. And if V in is equal to 5 volt, V out is going to be equal to 5 volt, thanks to the PMOS transistor. Okay, so that's what we use this. So we call this thing CMOS switch or CMOS transmission gate. Okay, so the pass transistor is used here. So we can use this as a logic also. You know, the output can be determined by this thing. So if this is Z, what is Z? What kind of logic is this? So if A is 0 and B is 1, output is going to be 0. So A dot B. If A is 1, B is 1, output is going to be 1. So this is the idea about pass transistor logic. But there is a problem here. If B is low, output is floating. So we need to then implement the other options. So I guess we better talk about this next hour. I'm going to stop here today. Okay. So do you have questions? About this?
No, hocam.
Okay, so this is an AND gate, but not really operating properly, because for the case where B is low, it's floating. So we need to make something about that part. Okay, see you next Monday then.
İyi günler hocam.
İyi günler hocam.
İyi günler.
İyi günler hocam.
Hmm.